Hello, this video is about enthalpy, which is OCR A Level Chemistry 3.2.1 from the specification, or Chapter 9 from the textbook. Enthalpy is a measure of the heat energy in a chemical system. Now that phrase might seem a little bit frightening. It can be more simply thought of as the energy stored within bonds. So you all, I hope, are aware of the idea of a fuel. A fuel would be a chemical that if you react it with oxygen, you can get heat given out. The energy hasn't just been created, the energy has to have existed, and it has come from the fuel and it has been stored within the bonds. So you would have covered this in GCSE in terms of energy changes. Enthalpy is just a new word for this specific form of energy, this energy stored within bonds, or the heat energy of a chemical system. And it gets the symbol H. We, unfortunately, aren't able to just measure the enthalpy in something. I couldn't give you 1 mole of coal or carbon and ask you, or anything, and ask you how much enthalpy it's got. But what we can do is we can look at the enthalpy change that accompanies a reaction. So the symbol for that is delta H. This triangle is the Greek letter delta, or D. And the units that we measure these in, because it's energy, it's joules, but it's often quite a large amount of energy, so we're going to do kilojoules. And then we have to do it comparatively to be able to compare different chemicals, and of course it's the mole is our standard unit there. So the units for enthalpy change are kilojoules per mole. And to find enthalpy change, you look at the enthalpy of the products and you subtract from that the enthalpy of the reactants. Now again, there is a slight problem. We cannot just simply, for any given reaction, look up in a data book what the enthalpy of the products were and what the enthalpy of the reactants were. But we can measure this part here, the delta H. We can work out enthalpy changes because of the idea of conservation of energy. If you want to pause and see if you can remember what that means, that might be a good idea. So conservation of energy is that energy cannot be created nor or destroyed. So if you did a chemical reaction, all of the energy change that you can measure is coming from this. You're not just magicking up some new energy. What instead you can find happens is that energy can be transferred between the system and the surroundings. Now, for the purposes of this, a chemical system is all of the chemicals that are involved in a reaction, so all of the reactants, products, and the surroundings is essentially everything else. So if you did a reaction in a beaker and you had some water and you dissolved 2 chemicals in that, water would be the surroundings. Although of course the beaker itself, and then the air in your room, and then, well, the entire universe would be the surroundings. Now, I'm hoping that you can remember the couple of really key words from GCSE. The first one is exothermic. If you want to pause and see if you can fill in what the gaps would be, that would be a great bit of revision for you. So an exothermic reaction is when energy is transferred from the system to the surroundings. If we are to measure temperature change, let's say we had that reaction I just talked about where you've got your beaker and you've added 2 chemicals to each other in the water, you could put a thermometer in the water and you could measure the temperature change. And if energy was transferred from the system into the surroundings, into the water would get hotter. So the way to think about this, exo means, well, to exit or to leave, and heat is leaving the system, so therefore the surroundings get more energy and they become warmer. So again, if you want to pause and try and figure out what the opposite of this would be, do so please. So the opposite, if we write it down, energy is transferred from the surroundings to the system. That would mean there would be less energy in the surroundings and they would actually get colder. So any reaction where the surroundings get colder, this is what's happening, energy is going into the system, it's not just disappearing. And the opposite of exo is endo. So an endothermic process is one where energy is transferring into the system. There's more energy in the bonds of the products than there was in the bonds of the reactants. Right, let's try and represent this in a diagrammatic form. So we've got some axes here. The first one, so on our vertical axis this is going to be enthalpy, and our x-axis, our horizontal, is progress of reaction. And this is essentially meaning the passing of time. So you start off in a reaction with the reactants, and over time you will get products. So in the simplest one I'm going to do here, in this reaction, the products have got less energy than the reactants. That means that energy must be transferred from the system to the surroundings. This difference between the two sets of chemicals is the delta H. It's the change in enthalpy. Again, we can't put an absolute number on this, nor this, but we can measure what's coming out. What we can also see here is that the enthalpy initially is higher than the enthalpy afterwards. So this, as we discussed, would be an exothermic reaction, and here delta H is negative because there is a decrease in enthalpy. It is going from the system to the surroundings. The energy in the surroundings is not called enthalpy. Enthalpy is a specific term for the energy in the bonds. However, it's not quite as simple as what I've just drawn there. There is something else that has to happen. If you want to pause and see if you can remember this from GCSE and even attempt the diagram yourself, that would be worthwhile. Welcome back, or just hi from an awkward pause. So afterwards, again, same setup as before. The products have less enthalpy than reactants. They're lower down. However, to get a reaction to take place, we need to break some of the bonds in the reactants, and this requires us to put energy in. So I'm actually going to draw this hump, and if you view the progress of reaction as from the start, you have to go along, and then you actually have to put energy in before you can reach the products. And the way that we represent that is to extrapolate with a dotted or dashed line, and you're going to draw a single-headed arrow. Now, you are a teenager, and for some reason you're going to want to represent this with a double-headed arrow. I don't know why it happens to all of you. Please try to grow beyond this. Single-headed arrow, and it's from the energy of the reactants to the crest here. I'm going to put a little asterisk because I've got no space. That asterisk is what's called the activation energy. And activate means to start something. It's the energy required to break bonds to start the reaction. And you'll notice that that is always an endothermic process. You have to put energy in to get something started. Simplest one might be to think about a match. You strike a match, and that energy that you're putting in, the kinetic there, is enough to overcome the activation energy for the match head's chemical, which is a very low activation energy. If you just rub a piece of wood, you're unlikely to make it warm enough that it will start to combust. But the materials that coat the match head, you can, from that friction and from that kinetic energy, and then the energy that they release is enough to then provide the activation energy for the future combustion reaction. Now, this works both ways. Again, I've set this up. Now, I'm going to put in products being higher in energy than the reactants. There is still an activation energy, and it goes above both. We draw the activation energy in the same way. We extrapolate out the reactants, and it's the difference between where the reactants were and the top of this peak here. So this is again the activation energy. This final reaction here is endothermic. We've got more energy in the products than the reactants. The previous one was exothermic. And the way that we can represent these is to again extrapolate the line of the products, and you can do again a single-headed arrow, and it's always from the reactants to the products. For the exothermic, the arrow is pointing down as there is a decrease in enthalpy. For the endothermic, the arrow is pointing up because there is an increase in enthalpy. Right, final part for this intro video. You need to know a few specific versions of enthalpy change. I'm going to give you a run through a couple of them just now. The first one is this lovely symbol here. Triangle, lowercase f, capital H, London Underground sign in a superscript, or delta FH naught. This is what's called the standard enthalpy change of formation. You have some great news. You need to learn this definition. So, all of the definitions for enthalpy changes, you need to define how much of the thing and what's happening to it. So, they always start off the enthalpy change that occurs when, or the enthalpy change that accompanies. And the first thing you're looking at is the amount. And there's almost always 1 mole. It's just being specific about 1 mole of what. So for enthalpy formation, it's the enthalpy change that occurs when 1 mole of a compound is formed, hence the formation, from its elements, and this is crucial. So if you have any compound in the world, you just look at its formula and figure out which elements are in it, and that's how you would get there. So let's try this. For water, the formula is H2O, and the elements are H2 and O2. Now, I can only make 1 mole of water, so therefore I need half a mole of O2, because a half of 2 is 1. And so there we go, that's the first part of this. The next bit before I go on is this little symbol here, and this means under standard conditions. And there's a second part to this, with all reactants and products in their standard states. If you have an exam question that asks you for 3 marks to define these, you will need to define the standard conditions. So the temperature, the standard temperature that's given is 298 kelvins, which is the same as 25 degrees Celsius. And then the pressure is 101 kilopascals, which is 1 atmosphere. Technically, we really should say 100 kilopascals, but all 3 of these get accepted. Pick one. Best one, but this is the one that quite often you will see written down. So, at 25 degrees Celsius, which is a fairly warm room temperature, certainly not a classroom in lockdown, and 1 atmosphere, your standard states are the states that they would be. So here, water is a liquid, oxygen, well, first off it's O2, and then it's a gas, and hydrogen is H2 as a gas. So that's what you'd have to do, and you're going to have to do a little bit of practice for each of these. Final one for this video is delta C H0. So again, standard from this bit, enthalpy here, change, and the C stands for combustion. You need to get this definition spot on. So it's the enthalpy change that occurs when, again, it's going to be 1 mole. Now last time it was a compound you were forming. Now you can burn an element, so we just simply put a substance. But we can't just put burning 1 mole of a substance. There's a specific thing we need to get in, and it's that it reacts completely with oxygen. So if you had carbon reacting with oxygen to form carbon monoxide, that would not be the standard enthalpy change combustion. That's incomplete combustion. So this reacts completely is crucial. The typical answer from a year 12 does not have that included. And then we follow it up again with under standard conditions with all reactants and products in their standard states. So if we give an example, methane is CH4. We're going to react it with oxygen. Right, well we better go through some standard states. Methane is a gas at standard temperature and pressure, so is oxygen. We have to react completely, no carbon monoxide, we're going to have to get all the way to carbon dioxide. Oh, that's a gas at room temperature. Despite the fact that if you burn methane, you're going to get water vapour, we're assuming that all of this is immediately reverting to 25 degrees Celsius, so we have to put H2O in as a liquid. The examiners will love to try and trip you up with this. Watch out for that one. And then I'm just going to try and balance the equation. I can't multiply the methane by anything because I need 1 mole of the substance. So the 1 carbon to 1 carbon is great. 4 hydrogens. Chuck a 2 in there. Sort all this out. That is the standard enthalpy change of combustion for methane. Thank you.